New chapter, elements and compounds. We have mentioned atoms before. The atomic theory has been around for a very long time. The atomic theory says that all matter, anything that occupies space and has mass, is composed of atoms. These are the tiny little building blocks that make up everything. Why is that important? Well, because if we understand how the smallest little tiny units that make everything up behave, we can start to extrapolate that. We can work our way out to bigger and bigger things and understand how the bigger things are going to work. The way that those atoms behave determines the way that bigger things will behave. An atom is the smallest unit of an element. Anything that's on the periodic table is an element. We have 118 options. Most of those do exist right now. Some of them might exist somewhere. For the periodic table we have in the class, if it's filled in, that means that it exists right now. If it's not filled in, that means you have to make it in a very expensive lab, and then it disappears almost immediately in some cases. So that's our smallest unit, is an atom. Once you get down to the atom level, you can't break it down any further. You can't break that element down any further. That's our smallest piece of an element. And we have 118 known and named elements. Atoms are very small. The largest atom, the biggest atom, has an approximate diameter of this really small number, 5.4 times 10 to the minus 10 meters. So if you take the width of your little finger, which is maybe a centimeter, depending on your hand size, you'd have to line up 18 million of them end to end just to get across the width of your little pinky finger. So they're super, super small. As I mentioned, this idea has been around for a long time. Leucippus and Democritus, both in the BCE era, so like 2,400, 2,500 years ago, had ideas about atoms. Democritus, pictured in this painting, suggested that if you divide things up smaller and smaller, you cut something in half, cut that in half, cut that in half. If you just keep doing that over and over, eventually you have to end up with something that's the smallest thing. You can't just keep, dividing it forever. And that's where we get the name atomos, or atoms. It just means indivisible, which is sort of true. Those ideas floated around for a really long time, and then more than 2,000 years later, John Dalton, founder of the Dalton, came up with this atomic theory. We've got 3 points to Dalton's atomic theory. The first is that an element is composed of atoms, and those atoms are indestructible. So that's the ideas of Leucippus and Democritus. All the atoms of a given element have the same mass and other properties. So if you take one atom and another atom, they have the same mass and the same properties, that's the same element. That's what makes them the same element. Basically just meaning that, all the atoms in an element or of a type of element are the same. And atoms combine in simple whole number ratios, like 1 to 2, 2 to 2, 3 to 4, things like that, not 2.5 to 1, to form compounds. And those compounds are groups of atoms. Sometimes they are completely stuck to each other. Sometimes you can separate them somewhat easily, like if you dissolve salt in water. But the idea is that we're combining those atoms together, and they have to be whole number ratios. have a not whole number ratio? Why can't we have like a half?
Can't be separated through normal means.
There we go. We can't separate our atoms, right? We can't break our atoms down any further. So just like if I grouped up pairs of students, right? I can't cut a student in half, or I'll go to jail. So like I could make a group of students where it's 2 students from the left side of the class, 1 student from the right side of the class, 4 from the left, 4 from the right. I could do any sort of whole number ratios. If I try to take half a student from the left side of the class and combine that with 2 students from the right side of the class, it's not going to work. I'm going to jail. If I was a magician, I could do it. I'm not. So there we are. So those are the ideas behind John Dalton's atomic theory. And we have evidence, good evidence even, for the atomic theory. Back in 2013, high school, am I right? Scientists at IBM Research used a special microscope called an STM, a scanning tunneling microscope, to move carbon monoxide molecules. So the picture that you're seeing here is one frame out of a 60-second stop motion film, and each of these dots is a carbon monoxide molecule. So they took these carbon monoxide molecules, cooled them way down so that they didn't move around, and then just pushed them around with this tiny little needle to make a stop motion film that you can watch. And so that's the record for the smallest film, movie or whatever, 45 nanometers by 25 nanometers. Nanometers being 10 to the minus 9 meters, really small stuff. Atoms, as it turns out, are actually made of other stuff. You can break them into pieces. And those pieces of the atoms are listed here. We've got our big boys, protons and neutrons. They're very similar in terms of their mass. Electrons are very small. They're much less massive. And we have a unit. It's actually the unit that shows up on the periodic table, the atomic mass unit, that's defined based on a carbon atom. It's 1/12 of the mass of a carbon atom that has 6 protons and 6 neutrons. So on the periodic table, the number under each element symbol is in AMUs. Or is in AMU. So good to know from this are 3 particles, their names, proton, neutron, electron. And you can also see they have standard symbols, their mass in terms of AMUs, a relative mass relative to the proton, and they have different charges. The proton is positive. The electron is negative. And the neutron, conveniently, the neut-er part, like in neutral, 0 charge, neutral. Pro, like as in favor of something, and electron, like the modern version of negatron, which, negatron like negative. Why they switched, I don't know, but that's what we have. Okay, comparing our protons and our electrons. The proton is nearly 2,000 times more massive than an electron. That's what this 0.00055 relative mass for the electron is. So if our electron is a 20-pound watermelon, that's the smaller one, any guesses on what our proton is? What's 2,000 times bigger than a 20-pound watermelon? Any guesses?
40,000.
Like, what's an object of that size? Or of that mass? It is a semi-truck. So if our electron is a 20-pound watermelon, the proton is a 40,000-pound semi-truck, which I think is halfway to maxed out in terms of their legal mass. The other comparison is that if the electron's a grain of rice, then the proton is a baseball, but I feel like a watermelon and a semi-truck is just like, they feel so much bigger in terms of that difference. All right, in our atoms, in our elements, we've got different numbers of different subatomic particles. Our subatomic particles being the protons, neutrons, and electrons. We're going to talk about protons first. So the number of protons has a very important function. It identifies it as a particular element. Element identity is based on the number of protons. So the number of protons that an atom has makes it whatever element. And we call that the atomic number, and it has the symbol Z. So Z is our number of protons. Some examples of elements with different numbers of protons include sulfur, usually stinky, or at least doesn't smell particularly good. Silicon, like is in your phone or in your computer. And gold, like might be on some of your jewelry. Also in your electronics. And it's the number of protons that makes it that element. Our periodic table lists all of our elements based on their atomic number. Our atomic number is that number up on top. On our periodic table in the class, it's in the top right corner. And it counts up as we move left to right and then wrap around. And we skip over that weird jump in the middle. So our first is hydrogen, then to helium. From helium, we skip all the way out to lithium. So it wraps around. And then we work our way left to right, working in that same row. Once we get to neon and E, we jump back around to sodium. And it counts up, and it continues that way. We also have this weird set of extra stuff that gets pulled out and put down below, lanthanides and actinides. You don't really need to worry about those too much, at least for this class. Questions so far? What's an atom? What are subatomic particles, elements, etc.? All right. So we just learned atomic number. Which has the symbol Z, and it's the number of protons. We have another important number when we're talking about our subatomic particles, our protons, neutrons, and electrons, and it's our mass number, A. Our mass number is the number of protons plus neutrons. Why don't we include the number of electrons? Any ideas? It's not that they're negatively charged.
They're not in the nucleus, and there's isotopes, so the number of electrons can vary.
They're not in the nucleus. That's probably not part of it. We will get to isotopes. They have almost no mass. That would be my guess, or one of my guesses. They're just super, super small. Like if we were trying to count the mass of our fleet, and we, for some reason, have 50 semi-trucks in our fleet, and also 4 watermelons. Watermelons aren't good at transport. We wouldn't count the watermelons because they're so small. We would just add up the mass of our semi-trucks And the mass of our watermelon would kind of be within that, like whatever plus or minus our scale has. It's negligible. Our mass numbers also help isotopes. An isotope has to do with the number of neutrons. So if you change the number of neutrons, it's a new, what we call, isotope. An isotope has the same protons, so it's the same element, just a different number of neutrons. And we can calculate the number of neutrons in an isotope in a particular flavor of an element, basically, by subtracting the mass number being protons plus neutrons. If we subtract out Z, which is the number of protons, then all we're left with is number of neutrons. So that's 2 of our subatomic particles. Helpful and related to that, getting us into isotopes and being able to describe different isotopes, different flavors of a particular element, are element symbols. Our element symbols are unique representations, like state codes, for identifying a particular element. There are 1 or 2 letter abbreviations. First letter is always capitalized. This is especially important if we were, for some reason, dealing with something like Cn, capital C, lowercase n, which I believe is copernicium, number 112 on our periodic table. That is not the same as capital C, capital N, because capital C, capital N is carbon and nitrogen. Some of these names make sense. Others don't make quite as much sense because they're based on a historical name. Like natrium is one that you might have seen in the news recently because Bill Gates made a new natrium nuclear facility or something like that. I haven't looked into it, but natrium just means sodium. And we get that Na symbol from the old name natrium, potassium from kalium. So it has the symbol K. 2 of these that I've got, ways that I remember them, are lead, Pb. What's a food that starts that we would call Pb? What is that? Peanut butter. Not peanut butter, peanut butter. And when I think of peanut butter, at least in this context, I think of how thick it is. Like you get it in your mouth, you get it stuck to the roof of your mouth, and you have a hard time getting it out. It's kind of thick and creamy. And lead, as far as metals go, is also sort of thick and creamy. It's kind of easy to work with. You can kind of cut through it. So that's how I remember lead and peanut butter. Hopefully you don't have lead in your peanut butter. The other one that I have a remembering thing for is tin. There's a tool that's used for cutting sheets of tin. Does anyone know what that tool is called? Tin snips. SN, like starting off snips, so tin snips. So that's a little insight into how my brain works. All right, if you have your yellow sheet will come in handy here. find the name and atomic number for each of these elements on your periodic table. All right, who's got the name for Na? Sodium. Where can we find sodium on the periodic table? Kind of in that top left side. Let's see. Right up there, Na. Atomic number is what for sodium? Our atomic number Z is 11. How about changing our second letter to Ni? What is Ni? Nickel. Where can we find nickel? Sort of in the middle, right? And what's our number for nickel? Our number for nickel is 28. It's that upper right-hand corner, or top number. How about for P? What is P? Yeah, phosphorus. And that's in the upper right-hand corner of our periodic table. And what's our number for phosphorus? 15. And the last one, Ta. What is Ta? Tantalum. And what's our number for tantalum? 73. We've got tantalum kind of in the bottom left area, number 73. Questions about any of those? Generally, the periodic table that I give you on the exams has the names written out with the symbols. However, it would be helpful for you to have practice with the symbol and the name, going back and forth between the two, because when we're writing out names or when we're trying to figure out how to talk about a certain chemical formula, that can be very helpful to have. Okay, so we can see that the periodic table is in kind of a weird setup. If we condense the first 20 elements, or first 18 elements down, this is what it would look like. Dmitry Mendeleev, who has a periodic table element named after him, proposed the periodic law that if you arrange the elements in increasing atomic number, or at least an increasing relative mass, certain sets of properties are going to show up periodically on a regular basis. And that's how we have the periodic table that we have now, rather than just like listing them all out in a big rectangle or something. We've got them set up so that if you know how to manage, if you know how to work your way around a periodic table, like you're going to learn in this class, you can take a look at the periodic table and know certain things about how each element behaves, rather than just laying them out in a long line. That kind of loses some of the meaning. So the periodic table is actually value added into it that we're going to be talking about and using for this class. that periodic law is a law. It's based on observations. And it doesn't tell us why those properties recur, why they show up every so often. It just tells us that they show up every so often. Another fun fact about our periodic table, it's broken down like this. So if we take off all the symbols, all the names, we can break it down into things that are metals, things that are nonmetals, and things that are semi-metals. These are sort of metals. They've got some of the properties of being metals, but also not all of them, but more so than our nonmetals. And generally, metals are on the left side. And nonmetals upper right, mostly. So it's a bit of a generalization. And then in between our metals and nonmetals, we've got our sort of metals, our semi-metals, that are just kind of like sort of along this kind of diagonal line. You've got a diagonal line on your yellow sheet that kind of things that are on that diagonal line could be in that semi-metal category. So our metals take up most of the periodic table. They've got a lot of similar properties, things that we know metals for. They're good conductors of heat and electricity. Right, copper famously good at doing both of those things. You can pack them into flat sheets and other shapes. You can pull them out into wires. There's a reason why our wires are made of metal, because you can pull them into wires. And they're often shiny, not always, but they can be made to be shiny. Hopefully, all things that you know about metals already. And another important fact about metals is they tend to lose electrons. We haven't talked about electrons much yet, but we will get to that. And they tend to lose electrons if they go through chemical changes. So when they go through a chemical reaction, metals typically just say, yeah, go ahead, have my electrons, I don't care about them. Examples include things like iron, magnesium, chromium, sodium. Pretty much if it's in that like middle rectangle or further left, those are all metals. Some of the stuff to the right of that middle block, some of these things like tin, right, those are also metals. Also on our periodic table, another way we can group things is as nonmetals. Nonmetals, their properties are a little bit more varied. Some are solids at room temperature. Others, many of them are gases. For our periodic table in the class, if it's got a black filled in symbol, that's a solid at room temperature. If it's blue, that's a liquid. If it's red, that's a gas. Nonmetals tend to be bad conductors of heat and electricity, unlike metals. And perhaps most importantly, they tend to gain electrons when they undergo chemical reactions. Examples of these include oxygen and nitrogen, which we're breathing right now, and chlorine and iodine, which I don't think we're breathing very much of right now. Fingers crossed. And then our last and weirdest group are the metalloids, also called semimetals. These display mixed properties, sometimes really weird properties. They're also sometimes called semiconductors. So like the silicon that's in a lot of our electronics is a semiconductor. It's a semi-metal or a metalloid. Metalloids include silicon, arsenic, and germanium. So those are kind of the weird ones out. And a little bit less clear where they are on the periodic table. They're just kind of wedged in between there. All right, let's classify some elements as metals, nonmetals, or metalloids. First one up, Se. Se is selenium. It's up here in the top right of the periodic table. Any guesses on what Se selenium is? We've got a guess for nonmetal. Any other guessers? Nonmetal is a great guess for selenium. Next up, we've got Mg, Mg number 12, magnesium, all the way on the left side of the periodic table, kind of in that upper left corner. We've got a guess for metal. Anyone else agree? It is a metal. It's on that left side of the periodic table. And then we've got germanium, Ge, showing up at 32. Guesses? Got guesses for nonmetal, metal, metalloid? We've got them all? Yeah, I would call this a metalloid. And then the Attorney General, where is it? Number 47, Ag. What do we think? Is that a metal, nonmetal, metalloid? It's a metal. It's silver. We know silver is a metal. So sometimes the ones that we recognize can be pretty easy to place them even if we can't find them on the periodic table. Somebody asks you, what's titanium? That's a metal, right? You don't even have to look and find it on the periodic table. It's number 22. Some of those, kind of a gimme, it's a freebie, because they're things that we know. Questions about classifying our elements so far? All right, another way that we can break them down, not by just metal, nonmetal, metalloid, we can also break them down by where they show up on the periodic table. We've got two groups. One of them is our main group, and one of them is our transition elements. So that weird wedge in the middle, that's our transition. And then our main group is our first two columns, or groups, and our last 6 columns are groups. And then we also have our weird ones out, the lanthanides and actinides. We don't really talk about them very much in this class. So transition metals in the middle, and then our split 2 groups that make up our main group elements. There's a reason why we separate them out this way. And a big reason for that is that our main group elements have predictable properties. Our transition metals, not so much. Our transition metals are a little wonky. I took a whole graduate class about transition metals, if that gives you an idea of how wonky they are. A whole class just about transition metals. This gray unlabeled lump, that's other stuff. So things that aren't in the far right 2 groups. So looking at the groups with, or the columns with 13 to 16, some of those have names, but they might just be like the boron group, the carbon group, nitrogen group, oxygen group. Nitrogen and oxygen group do have names, but we don't really talk about them much. I will mention them at some point. So each of these columns Column is another word for family or group. Those all mean the same thing. They're referring to the same up and down set of elements on the periodic table. And several of those have names. The first of those that has names, we're going to work our way from, it might be left, then all the way, anyway, we're going to work our way through them. Our first one up, the first column, are alkali metals. You just kind of have to memorize the names of these. So alkali metals, group 1A or 1. A in this circumstance means main group. So column 1 in our main group. These are alkali metals, and they are very reactive metals. You can watch YouTube videos of people making these light on fire or blow up. And these get more reactive as you go down. Which is kind of just a for fun fact. The most reactive in this group is actually cesium, even though francium is below it. Francium doesn't exist in very large amounts, and it's also, for some reason, less reactive than cesium. So those are our alkali metals. Moving one spot over are the alkaline earth metals. So we've added Na-earth to the alkali metals. 1 alkali, 2 alkaline earth. 2 is bigger than 1. The name for group 2 is bigger than the name for group 1. Might help you keep from getting them confused. These are fairly reactive, but less reactive than alkali metals. And it's beryllium and everything underneath it. Another important named group is our halogens. So we're skipping over to group 7A or 17. So things from fluorine down to what here is UUS, but on the slide is tennessine. Tennessine was in the last group of elements to be named in 2016. So the halogens, like in halogen bulbs, I'll say in some light bulbs, halogen lamps, are very reactive metals. And then the last named group that we'll talk about are the noble gases. And the noble gases are inert. They do not react, pretty much as a rule. If you can get a noble gas to react, it will almost immediately go back. It'll say, no, I don't like this, I'm out, and immediately revert to being a noble gas.
I got a question.
Question?
Hold on, I'm trying to phrase it right. Does the reactiveness of an element, is it based off of how many electrons are in its outer ring, how needy it is to lose or gain an electron to complete that circle?
Yes, and we'll get to that in a couple chapters.
Okay. And that's why noble gases aren't really reactive, because all their rings are satisfied.
Correct. Yeah. For the rest of you, don't worry about it. We'll get there. So these are our noble gases. Recognize helium, like we use in balloons, is on there. That's part of the reason that you can breathe in helium without, like, killing yourself or whatever. Breathe it in from a party balloon and then speak, and then your voice gets pitch shifted up. That's part of the reason for that. All right, which group or family, some of them are named, some of them aren't, does each of these elements belong? We've got Li. Where's Li on our periodic table? All the way over on the far left side. What number do we see up on top for the group for Li? 1. It's in group 1. Does that group have a name? It is our alkali metals. And we've got Ar. Where's Ar on our periodic table?
Group 18.
The far right side, that's going to be our group 18. What's the name for group 18? Yeah, it's noble gases. That's argon. Why do chemists only tell bad jokes? Because all the good ones are gone. And then we've got chlorine. Where's chlorine on our periodic table?
Group 17.
Over in the top right-hand corner. It's in group 17 or 7A. What's the name for that group or column? Halogens. And last but not least, we've got SR. Where's SR on our periodic table? There it is. It's in group 2. And what's the name for group 2? Group 2 or 2A, that is our alkaline earth metals. Questions about groups or families specifically related to elements, not your own families? I'm not a paid therapist. Not a free therapist either. Alrighty. So we talked about changing protons, we talked about changing neutrons. Who remembers what changing a proton does?
Changes the element.
Yeah, it changes our element. If you change the number of protons, it's a different or new element. If you change the number of neutrons, what do we call that?
Isotope.
Yeah, we call it an isotope. New or different isotope. We've also talked about electrons, how metals tend to lose electrons or give electrons, and halogens and other nonmetals tend to gain or receive electrons. If you gain or lose electrons, then it becomes a charged particle called an ion. Ions are charged particles. Sure, it says it in the slide, but it's also there now with my handwriting. We've got positive ions. Positive ions are cations. We also have negatively charged ions that are called anions. it would be helpful to have those memorized. I'll even box them in for you. We'll show the charge of an ion in the upper right corner of the symbol. And we're going to write the magnitude, that's short for magnetic attitude, first, and then the charge afterwards. So not how we're used to writing numbers. So examples are barium 2+ and phosphorus 3-. I will talk through them in the direction left to right, so barium 2+ instead of barium +2. It's a convention. Anyone know why it's that way? Cool, I don't either. That's just how it's been done, so I assume that's why we keep doing it that way. I'm sure there's a good reason somewhere. All right, so ions, if we lose electrons. Lithium is a metal. Metals tend to lose electrons. Lithium can lose one electron to form lithium plus. The 1 is implied. That's a common theme when we're using symbols. So we just write lithium plus. You don't have to write in the 1. That's nice. It saves you a little time. The charge of the ion depends on the electrons that were gained or lost. In this case, we're losing electrons. We lost 1 electron. Losing 1 negative charge is the same as gaining 1 positive charge. You can also calculate ion charge. You take the number of protons. So let's look at lithium. Lithium has an atomic number of 3. That means it has 3 protons. If we lost 1 electron, then we would have 2 electrons. 3 minus 2, we've got a 1+ charge. You don't necessarily have to write this calculation. I understand that this is like a relatively simple calculation. Lots of you can probably do this in your head, no problem. So don't feel like you have to write it out every time, but if you need to assure yourself, that works. We can also gain electrons. Nonmetals tend to gain electrons. So let's say that fluorine gains 1 electron to form F- ions. Fluorine normally has 9 protons. We find fluorine in the top right corner. It's got an atomic number of 9, so 9 protons. We're saying that it gained 1 electron. It also would normally have 9 electrons to be nice and evenly balanced. But it gained 1, so now it has 10 electrons. 9 minus 10, we get 1-. So that's why it's fluorine with a 1- charge. Again, if you can just do this in your head, you see 9 protons. Protons are positive. 10 electrons. Electrons are negative. We've got 1 more negative than we have positive. So it's a 1 negative charge. Hey, that works for me. That's how I do it too. Or you can write it out. Either way, whatever works for you. Questions about changing our electrons? Elements normally have the same number of protons and electrons. Just writing that out because I don't think it was written out earlier. Might have been. I just missed it. So those normally have a neutral charge. Not to say that ions are weird, but typically we're going to have a neutral charge equal positive and negative. All right, back to isotopes. We talked about them a little bit. Isotopes occur when we change our number of neutrons. All atoms of a given element have the same number of protons, since the number of protons defines the element. But, contrary to Dalton's theory, they don't necessarily have the same number of neutrons, and therefore they do not have the same mass. Isotopes are naturally occurring. Or occur naturally. And they've got their own special ratio of how much of one isotope versus another isotope. For example, hydrogen naturally occurs as 3 different isotopes. We've got protium. Most of them don't have special names. Hydrogen has special names for it. Protium is what we think of as normal hydrogen. And then we've got deuterium, the deut part for 2, and tritium, the tri part for 3. So protium has just 1 proton. It's got a mass number of 1. Deuterium has 1 neutron, so it's got a mass number of 2, total number of particles in the nucleus. And tritium has 2 neutrons, so it's got 3 particles in its nucleus, in its center spot. How do we know how much of each occurs? If I asked you how much of hydrogen is naturally occurring as deuterium, how would you know that? You wouldn't. You'd go look it up. That's the same way I would do it. So you don't have to know, you don't have to like have memorized natural abundances of these things. It's a waste of time. You just look it up. When we're writing out isotopes, we've got this convention for writing out the isotopes. We've got our symbol in big, normal size letters, and in front of that we've got our mass number and our atomic number. Who remembers what our symbol for mass number is? I heard the 2 things that I was expecting to hear as guesses. Our mass number is A. So what does that make our atomic number? Z. Which one comes first in the alphabet? A, right? So A over Z. And if you can't remember A over Z, and you've got 2 numbers and you have to put them in front of your element symbol, A is always going to be bigger than Z, except in the case of normal hydrogen, because they'll be the same. So 4 over 2, it's always going to be big number over little number, or A over Z. So if you're not sure if you've got your mass number and your atomic number and you don't know where to put them, big number over little number and then our symbol. For neon, we've got 3 isotopes. We've got 20 over 10 with our symbol for Ne. We also have a version with 21 for the mass number and a version with 22 as the mass number. Why did we only change this top number?
Because the protons aren't changing, it's just the neutrons.
Yeah, it's just the neutrons changing. if we change the protons, if we went from a 10 to an 11, for example, 11 would be a different element. So instead of being neon, right, with the number 10, it would be natrium, sodium with the number 11. So that bottom number is linked to the symbol. So if you have one, you can figure out the other. And that'll be helpful at like the last week of class. So giving you an early start on that. So again, our mass number, that's just in case you forgot. We saw this earlier. Another way that we can do the notation is by putting the symbol and then following that with the mass number. Or we can write out the full name and the mass number. The reason that it's the mass number and not that other number is because we can get to that other number with the name or the symbol, right? Because those are linked, like we saw 2 slides ago. So we can work this into the other form if we have a periodic table, for example. Thought I had a sneeze. All right. What are the atomic number, mass number, and symbols? Give me all 3, please, for the bromine isotope with 46 neutrons. I'm going to give you some time to run your brains on that one, and then we'll come back together in like 2 minutes. All right, bromine. What is our 1 or 2 letter symbol or abbreviation for bromine? Br for bromine. And then we can find bromine on our periodic table. It's over on the far right side. It's a liquid at room temperature. It's got that number 35. What is that 35? Is it our atomic number, our mass number, or neither? Yeah, that's our atomic number. So our atomic number is 35. So check, we got our atomic number. We got part of our symbol. How do we get our mass number?
You add the protons
Yeah, mass number is protons plus neutrons. Protons plus neutrons, we figured out that our protons are 35. And we were given that this particular isotope has 46 neutrons. So 35 plus 46 should be 81. All right, we've got two numbers. We've got a symbol. Number goes on top. 81, big number up top. So 81 over 35, the symbol Br, that's one of our isotope symbols. Who's got one of our other isotope symbols? Another way that we can write it out.
BR81.
Yeah, BR81, BR-81, and then our last one, bromine-81. All three of these convey the same information. The top one is maybe a little bit nicer since it has that 35 explicitly written out. But once we get in the practice of it, it shouldn't take long to switch between those two forms, two types of forms. Questions? I'd like to point out something that will hopefully help with my sanity on a future worksheet. I wrote out bromine with the lowercase b. It's not a proper name, so it's lowercase. The symbol, always capital first letter, lowercase second letter. When we write it out, it's not capitalized. So please don't write it out capitalized, unless it's starting a sentence. That's the only time you capitalize it. Another thing that we can do with this fun knowledge that we have is we can take a symbol like 40 over 19K. This is a particular isotope of potassium, and we can pull from that, we can pull out information. So we can work backwards. So big number over little number, like it should be. And we want to find the number of protons. Should write that in the other color. And we also want to find the number of neutrons. One of these is right in front of us, and that's the number of protons. So 19 we have 19 protons. That's our atomic number. To figure out the number of neutrons, we're going to look to the other number, this 40. That 40 is our mass number. And mass number equals protons plus neutrons. So 40, which is our mass number, is equal to 19 plus the number of neutrons. If we want to be rigorous about our algebra, subtract 19 from both sides. The number of neutrons is equal to 21. Other fun stuff that we can do is determine the charge of ions. So let's say we have a cobalt ion with 25 electrons. we need to figure out what its charge is. One way to do that would be to look at neutral cobalt. Another way would be to look at the number of protons that cobalt has. Cobalt is CO, so we're looking for CO on the periodic table. It's got an atomic number of 27. So cobalt has 27 protons. Some of you might look at this and see 27 positively charged things, 25 negatively charged things, 25 of our positive things will cancel out. We've got 2 extra protons, and you'll come out that that's got a 2+ charge. That's great. Perfect. So CO, the little 2+. You might instead use this little ion charge formula. Ion charge is protons minus electrons. So it's 27 protons minus 25 electrons. So it has a charge of 2, and the plus is implied. If we somehow did our math backwards here, let's work in a hypothetical universe. We instead did 25 minus 27 equals 2 minus. There is a way that we can know that that is not correct. What kind of element is cobalt? It's a metal. Metals tend to lose electrons. Metals tend to form positive ions. So based on that, if we got a 2 minus or a 2 plus, that 2 minus, once we get this ingrained in our brains, once that becomes second nature, we would know that 2 minus, probably not correct. We might take another look at it, or we might decide we'll just go ahead and flip it. So it would be a 2 plus. All right, another one, iodine with 54 electrons. We need to find iodine. Iodine has the symbol I. It's number 53 on our periodic table. So 53 protons. Again, some of you might see 54 negatively charged things, 53 positively charged thing. That's in excess of 1 negatively charged thing, 1 minus charge. Or you might instead do ion charge equals protons minus electrons and get 53 minus 54 equals 1 minus, so it's I minus. Some people pronounce it iodine. I pronounce it iodine because fluorine, chlorine, bromine, iodine, astatine, instead of fluorine, chlorine, bromine, iodine. It just feels like it fits. Okay, last one before we wrap up. A nitrogen ion with 10 electrons. Nitrogen is N. It's up there. It's got 7 protons. It's got an excess of 3 electrons. So it is N 3 minus. Questions before we wrap up?
Attendance sheet today?
There's an attendance sheet floating around.